So good evening. Welcome to the closing roundtable. First, I would like to introduce our panel, which consists of 5 very distinguished mathematicians. On my far right, Lennart Carlsson, Professor Emeritus at the University of Uppsala and a former president of IMU. His research interests are in harmonic analysis and dynamical systems. Now, all of our panelists are recipients of many awards, and I decided that it would take far too much time to list them all, but I make an exception in reminding you that Lennart Carlsson was awarded this year's Abel Prize, for which we offer many congratulations. I would like to say how much IMU values its collaboration on several fronts with the Norwegian Academy of Sciences and Letters and the Abel Fund. So, next, Ronald Koifman, who is Professor of Mathematics and Computer Science at Yale University, and his research interests are in analysis, in particular harmonic analysis and wavelets, and applications to information processing. On my immediate right, Yuri Menin, who's Professor of Mathematics at Northwestern University, a former director of the Max Planck Institute of Mathematics in Bonn, and a former chair of the Fields Medal and program committees of the ICM. And his research interests lie in algebraic geometry, in number theory, differential equations, and mathematical physics. On my immediate left, Helmut Neunzert, Professor Emeritus at the University of Kaiserslautern. He's a founding member and former president of the European Consortium for Mathematics in Industry. And his research interests are in kinetic theory and fluid dynamics. And finally, on the far left, Peter Sarnak, Professor of Mathematics at Princeton University, and his research interests are in number theory and analysis. Just in case I betray at some point my own views on the subject of the roundtable, I work in nonlinear analysis, especially the calculus of variations and its applications to material science. By way of introduction, perhaps I can show the 2 earliest instances I know of in which the terms pure and applied mathematics feature in the literature. Oh, these were the panel. I forgot to do this. That's bad. Here's the first one, the first issue of the Journal für die reine und angewandte Mathematik, Kröller's Journal, which appeared in 1826. And the contents of the first issue is shown, and actually you can see several papers there by Abel. And 10 years later, the first volume of the Journal de Mathématique pure et appliquée, Liouville's journal, appeared. And here you see the papers are much more applied. The authors include Coriolis, Liouville, Ampère, Lamé, Jacobi, and Sturm. So these were not bad for first issues of these journals. The old volumes of these journals, incidentally, are retro-digitized and freely accessible, which is where I obtained these images. So pure and applied mathematics have been explicitly mentioned for nearly 200 years and were doubtless recognized as being in some way different before that, and our topic is whether they are drifting apart. Each of our panelists will give a 10-minute presentation, and then the subject will be open to the floor, and I hope we will have a lively discussion. So I ask Lennart Carlsson to begin.
So mathematics really has 3 different phases. So the first concerns general education, and mathematics is of course just as important as learning to read, and this is a very important part of society. And the second in relation to the outside world is mathematics as the language of science. And this is a way in which I'm going to use the word applied mathematics as the language of science. And the third aspect is, of course, a subject of its own right, a logical system. And this is what most of us who are here right now represent. And we must clearly understand that of the three, we are the weak part. And that it is absolutely vital for the continuation of our science that we love so much to stay with good relations to the other two aspects. So the answer to the question if the mathematics and applied mathematics are drifting apart, I would say that we should make every effort that it doesn't happen. And I would like to object somehow to the word drift also. We are not really jellyfish, but we can do something about this ourselves. So I should like to concentrate on the aspect of the issue as far as it concerns the teaching of mathematics. We like to talk about mathematics and applied mathematics in this order, which seems to indicate that applied mathematics is some kind of corollary of mathematics, and that we are looking for ways of applying this. And this, of course, is completely wrong from the point of view of history. Through the years, mathematics has slowly been being built from nature, and we have observed the remarkable fact that the laws of nature can be coordinated into groups, and they follow rules. This started with geometry, of course, and numbers. And then we all know how difficult it has been to make continuous, that is, movement into something logically reasonable. And it's been around only for like 200 years in a logical setting. If we take a subject like probability, it may show that I am old, but anyway, it has been built as a mathematical subject in my lifetime, really. And looking into the future, we can see new areas emerging where the mathematics is missing. And the most spectacular there is probably computer science. Nevertheless, teaching of mathematics has always been done in a deductive way, that one goes from the general to the special, either as a logical system or as being applied. And this, of course, is contrary to the traditional way of how things should be taught. Let me mention to you that this also has happened in my lifetime. When I started studying at the University of Uppsala in 1945, the first lecture was devoted to the Dedekind cut. And we defined continuous functions with epsilons and deltas. And we had axioms, and we had definitions, and we had Riemann integrability, and I don't know what. As the number of students have increased and their interest in the logical structure of the field has decreased, one has successively been cutting off these typically mathematical aspects of the mathematics teaching. And to put it in a striking way, I would like to say that it's only applied mathematics that remains. So, and we have, I guess all of us experienced how there has been pressure from other fields, I mean from physics or technical subjects or even biology, that they want to teach their own mathematics and that we don't teach in a relevant way. And I would like to say that I can somehow see their point, because we have not really made any real effort to implement any kind of inductive way of teaching. That is going from examples and cases and applications to the concept. And you would think that the use of computers would have changed this in a drastic way, but that doesn't seem to be the case at all. We are still fumbling for ways of using computers in the teaching. So my thesis here today would be to say that we should make a really concentrated effort to make our teaching into an inductive teaching. I mean, one can think of different ways of accommodating students with different interests. So I have made a short list of what one could possibly do to change here. One of the essential points is clearly the attitude of ourselves, so to say, and also of our colleagues. Everybody knows that many mathematicians are very disinterested in things which are not leading to theorems or news statements. And there is a skepticism among our colleagues in other areas that anything useful can come out of contact with mathematicians. And it is my real wish that you would all, or we would all, try to remedy this situation. So what could be done is, for example, I have made 3 points here. So the first is that one should have a closer contact with the between the teaching and the applied areas. At least in Sweden, most departments which are applied have separate buildings, and we don't really see them. I mean, the pure people stay in one area and the applied people stay in another area. And it would be my wish that people with applied interest would be involved already in the construction of and the teaching of the basic courses. And also one would need to change the curriculum in some suitable way and try to speed up the use of computers in the teaching. I mean, we should really accept the fact that most students are not really interested in mathematics. I mean, they are interested, well, many are interested in their lives, but some of them are also interested in other areas, and one should accept that. And we shouldn't try to put our values on people who don't really want them. You know, one could compare these people with how you learn how to drive. I mean, most people have no idea how the car works and why it works, but you can still use it. And it's similar with the people who learn mathematics. They only want to be able to read books or understand the formulas that they are taught in the other courses. And I think one shouldn't criticize this. One should accept that this is a very natural attitude. I mean, after all, mathematics, as we know it, is a rather sophisticated and not very applicable field. Also, there should be, for example, something like partial differential equations. Everybody should have heard about that. They are going to meet it somewhere else. And finally, there is a movement in the